This example shows, step by step, how to correctly model the interaction between a shell element and a solid element. In the case shown, we have a retaining wall. In green, the wall modeled was shell elements. In gray, the wall foundation modeled was solid elements. In the view, we can also see the applied load, a triangular distribution, typical of retaining walls. This represents lateral earth pressure increasing with depth. Opening the load cases menu, we see two load cases, dead and imp. The imp load case starts from the final state of the dead case. This ensures that, when the lateral action occurs, the structure is already preloaded with self-weight. This sequence is important. Preloading captures the stiffness and stress state under gravity before the lateral pressure is applied, which affects displacements and moments. Now, let's run a first analysis, with no further adjustments. This baseline calculation is useful to expose modeling issues before adding complexity. We can see that the number of null steps is increasing rapidly, which indicates that the program is struggling to make the analysis converge. Let's cancel the analysis to review the saved steps. This first run shows that the model is unstable. We observe excessive displacements and spurious rotations that confirm instability. When you see non-physical twisting at the interface, it's a strong indicator of kinematic incompatibility. Why does this happen? It stems from the nature of the solid finite element, which, in its formulation, has only 3 degrees of freedom per node, 3 translations. Meanwhile, shell elements carry bending behavior, typically represented by rotational components at their nodes. So, when a shell with out-of-plane displacement, caused by the impulse load in X, is attached to a solid that does not have rotational degrees of freedom, it becomes impossible, at the intersection nodes, to restrain the wall's rotation. In short, the interface can translate together, but it cannot transfer rotational continuity unless we add constraints. One way to solve this is to create a constraint for each set of 3 nodes along the base of the wall. Triplets give you just enough kinematic control to emulate local rotational stiffness without over-constraining the model. In this example, for simplicity and practicality, we will use a weld, which allows us to define a range that determines which nodes belong to a single weld constraint. The value entered here, 0.45, will be justified next. Using welds keeps the workflow clean and scalable across long interfaces, compared to manually building many individual body constraints. In short, the idea is that each set of 3 nodes behaves like a rigid body, independent from the others. This local rigidization is not global. It only binds those 3 nodes together, so the wall can still deform realistically along its length. This way, the 3 nodes working together force the inner node to develop rotational stiffness, driven by the vertical displacements of the outer nodes. Thus, we ensure a fixed base condition for the wall. Functionally, this mimics a kinematic link that transmits bending continuity from the shell into the solid foundation. The 0.45 meters tolerance should be higher than the maximum distance between joints that belong to the same constraint. In the image, we see 2 dimensions of 0.42 meters, so it is okay. But we must also ensure that the tolerance is lower than the distance between each group of 3 joints. And in fact, it is lower than 0.75 meters, so it is also okay. This avoids overlap between adjacent weld groups and prevents over-constraint. As a rule of thumb, set the weld range equal to or slightly above the largest spacing within a triplet, and below the spacing between neighboring triplets. Let's run again the model. After this change, the structure no longer shows instabilities and exhibits the expected behavior. The interface now transmits rotation consistently, and the wall foundation assembly behaves as a single system. The displacements are now reasonable for this case study. Check the maximum lateral displacement, the deformed shape, to confirm the response aligns with engineering judgment. We also observe a concentration of bending moments at the base of the shell element, which indicates a fixed connection between the foundation and the wall. That was all for this video. If you want to learn more about the weld constraint topic, please watch the video above.